Continuing on our discussion for the theory of linear equations, we've talked about the general idea of linearity. We've looked at linearly independent functions and how the Wronskian is important to characterize and test the linear independence of functions and solutions to differential equations. We then moved on and looked at the homogeneous linear nth order differential equation and proved some important theorems there, especially regarding the general solution. And now we turn our discussion to non-homogeneous equations. So as a review, what is a non-homogeneous linear nth order differential equation? It basically has this form. We'll be using the asterisk to indicate this equation so that we don't have to keep writing it. And what's important here is that g of x is not identically 0 on I. If g of x were identically 0, that would be homogeneous linear nth order differential equation. But we are talking about non-homogeneous. Nevertheless, the associated homogeneous equation, which is exactly this equation on the left, but with 0 on the right, okay, is very important. And we'll be using 2 asterisks for that. So basically, the associated homogeneous equation of the non-homogeneous equation that you see here is this. Okay, you just take g of x and basically set it equal to 0. That's called the associated homogeneous equation. It's very important because particular solutions to the non-homogeneous equation will basically differ up to a homogeneous solution. Okay, so that's why we're not really done with homogeneous equations. We still need them. In the language of differential operators, where L, the differential operator that we have here, the non-homogeneous linear nth order differential equation may be written this way, and the associated homogeneous equation is just setting g of x equal to 0. It's a more succinct notation. Very important also, for this section we will be assuming, unless otherwise noted, that the coefficients in this equation, in these equations, will be continuous. And we also assume that an is not equal to 0 for every x in the interval. So it's non-zero, okay? And that's also very important. So unless otherwise noted, we'll go ahead and assume these. And we've also seen previously how not assuming these can get us into trouble. So we'll have a long string of definitions here. The particular solution is any function y sub p free of arbitrary parameters, constants that satisfies asterisk, which is the non-homogeneous equation, is said to be a particular solution. So that's what a particular solution is. It's just a function free of arbitrary parameters. So no sort of wiggle room with the constants that satisfies the above non-homogeneous equation. The complementary function, okay, also another important definition. The general solution of the associated homogeneous equation, double asterisk, to the non-homogeneous equation, y complementary, is called the complementary function of the non-homogeneous equation, okay? And we're dealing with an nth order differential equation. So if you take a look over here, the associated homogeneous equation is nth order, and here we have n linearly independent functions, right? That's how we get the general solution. Again, using the theorem that we've discussed previously for homogeneous equations, we know if we have n linearly independent functions, then this is the general solution, okay? But the general solution of the associated homogeneous equation to the non-homogeneous equation is called the complementary function. Okay? So particular solution solves the non-homogeneous, and complementary solves the homogeneous. All right, so now we have this incredibly important theorem. Okay? General solutions of non-homogeneous equations. Okay? So non-homogeneous are sort of most general of the linear equations. Okay? So let yp be any particular solution. Okay? You just plug in yp into that non-homogeneous equation and you get a solution. Okay? Or in other words, L operating on yp gives you g of x. To the non-homogeneous linear nth order differential equation asterisk on an interval I. And let y1, y2, ... to yn be a fundamental set of solutions to the associated homogeneous differential equation on I. Okay? So we take the non-homogeneous one, we set g of x equal to 0, and we get the fundamental set. Okay, and what is a fundamental set of an nth order homogeneous linear differential equation? Well, it's a set of n linearly independent solutions to the homogeneous equation. Okay, that's why this n is important. Okay, it's not just some arbitrary integer. It also matches with the n of the order of the differential equation. Then the general solution, and what does it mean to be the general solution? The general solution is a solution that every other solution may be obtained from, the particular solution. So any particular solution may be obtained from the general solution by fixing the constants. Okay, so in some sense it encompasses all the possible solutions to the differential equation. Once we have the general solution, we have every solution. Okay, so the general solution is this. Okay, it is the general solution to the associated homogeneous equation, okay, or the complementary function here, plus that particular solution, okay, where these c's are arbitrary constants and yc is the complementary function of star. So proof. Let yp and yp bar be particular solutions of the non-homogeneous equation. Okay? And again, so these are just functions that solve the differential equation that we started with, the one with g of x. Okay? They solve that, and they're free of arbitrary constants. Okay? We're going to let u be equal to this. Okay, so we're going to subtract these from each other. And we're going to operate with the linear differential operator. Okay, that's associated with the non-homogeneous equation above on this, on u. So we get a difference. By linearity, we have this. Okay, so that's where linearity slips in. But each of these is a particular solution, so each of these will be g of x once operated by L. And we subtract them and get 0. So what does that mean? That means that u is a solution of the associated homogeneous equation. Okay? And once we find a solution to the associated homogeneous equation, we know from our previous theorem on homogeneous equations that we could find some constant c to express u in terms of that, okay? Because it's the general solution. Any solution may be expressed as a sum of these basically a sum of constants times the functions in the fundamental set, where these constitute the fundamental set. So what do we say here then? Yp bar minus yp is equal to u is equal to this expression, right? We were able to do this from our theorem with homogeneous equations. And so y bar p is equal to this function plus yp. And what's the general idea here? Okay, the above theorem states that the particular solutions at most differ by a homogeneous solution. Okay, the homogeneous solutions get annihilated by L. L operating on a homogeneous solution gives you 0. So what this theorem is kind of telling you that once you find one solution of the non-homogeneous equation, at most another solution will differ by a solution to the homogeneous equation. Okay, it's kind of like adding 0 to a solution, right? But here 0 is not exactly 0. It's solutions to the homogeneous equation. And why is that? Because they get annihilated to 0 by the linear operator. Okay? And we could see that here. So, if you have some particular solution, you have, any solution that's expressed in terms of the complementary function, which encompasses all solutions to the homogeneous equation, then operating, because we're dealing with linear equations, we have this, and we get 0 there. Okay? So that's why it works. Okay? And so this is our most general solution. And this is exactly how we will solve these differential equations. What we're going to do is find any particular solution. Okay? No matter what. As long as it works, it works. So we're going to find a particular solution, and then we're going to find solutions to the associated homogeneous equation. And then we know we got our most general solution, which encompasses every possible solution, by adding the most general solution to the associated homogeneous equation to the particular solution to the non-homogeneous equation. And in that way, we characterize all possible solutions. And remember, this is general, so there are no singular solutions. Solutions that show up as not part of this n-parameter family. And that's very important. And this is why linear equations have this special status with differential equations. So let's look at an example. Find the general solution of this third order differential equation, non-homogeneous differential equation. Okay? So we'll talk more about how to actually get the fundamental set, but for now, just assume that you have that fundamental set right there. Okay? And you could check that it's a fundamental set. How? By plugging them into the Wronskian. Right? So you get the Wronskian of them, you show it's non-zero. And that is the case. And so these are the fundamental set for the associated homogeneous equation. And, again, we'll talk about solving the higher order differential equations, but assume that we were able to guess a particular solution here. This equation satisfies the assumptions that we have above of an not being equal to 0 and the ai being constant, and it is linear, it's clearly linear. Then we know that the most general solution, right? The general solution is going to be the complementary function, which is this 3-parameter family of solutions, plus the particular solution. Okay? And now any function that you plug into this differential equation and ends up solving it, then it could be expressed in this way. Okay, we would just have to fix C1, C2, and C3. And that's why general solutions are important. So we've talked about the superposition principle for homogeneous equations, and now we'll talk about it for non-homogeneous equations. And they're really quite different, okay, even though they're both superposition principles, but they sort of act in a different way, okay? So let y p sub 1, y p sub 2, dot, 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 y p sub k be k particular solutions of the non-homogeneous linear nth order differential equation asterisk on an interval I, corresponding in turn to k distinct functions g1, g2, dot, 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 gk. Now that's kind of confusing. What does that mean? That is, suppose y p sub I denotes a particular solution of the corresponding differential equation that we see here. So we have I different, okay, or k different non-homogeneous differential equations, okay? They each have the same coefficients, but they differ by what they equal, okay? So you have g distinct functions in general, okay? Then yp equal to the particular solution of the first one, the one where that has g sub 1, yp sub 2, which is a particular solution with g sub 2 there, okay, plus dot 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 yp sub k, which is a particular solution to the kth, okay, one where you would get that kth equation, is a particular solution of this non-homogeneous differential equation with them being summed, okay? So if you have particular solutions summed together on the right, all right, if you have the particular solutions summed, they give you a particular solution for these for this non-homogeneous one with the g's being summed. And the proof here is important because it kind of gives you insight of why that works. So the differential operator acting on yp, and yp is the sum of these particular solutions, one for each non-homogeneous equation. Okay, you operate on them. By linearity, you get this. And then L operating on yp sub 1 is g1. L operating on yp sub 2 is g2. You add and you get, and L operating is gk. And so you see here then that yp, where yp is equal to this sum, satisfies the non-homogeneous equation with these g's being summed, okay? And there's nothing special about just the sum. We could have also done this with constants multiplied, as we'll see. So it's best to see this through an example. So suppose that yp sub 1, okay, equal to negative 4x squared, is a solution to that homogeneous equation that you see here, okay? So let's kind of circle these, okay? Those are associated with each other. And yp sub 2 is a solution, particular solution to this non-homogeneous equation that you see there, okay? And yp sub 3 is a solution to, well, let's draw that. Okay. Then notice something. We have the non-homogeneous equation here, and on the right hand side we have the same right hand side with 2e to the 2x there in blue. In green we have that right there, and in pink we have that right there, okay? And now we want to find a solution to this new non-homogeneous differential equation, where basically the right-hand side is the sum of the right-hand sides of all the other ones, okay? So just to use the language of operators, let L be equal to d squared minus 3d plus 4, which is just transforming, you know, here's the second derivative, so, and minus 3, first derivative is there, plus 4, it's there. And let yp be the sum, okay, of yp1, yp2, and yp3. So in colors, we have this, and that, okay? And notice, we get the same thing here, right? What you see here, here's the pink y particular associated with the pink right-hand side g, okay? Here's the blue particular associated with the blue g, and the green particular associated with the green g, okay? And why this works? Well, let's operate with L. By linearity, we have this, and we know because L operating on yp1, L operating on this, gives you this g, this right-hand side that you see right there. And the same thing with the blue, okay? L operating on this will give you this right-hand side there, and that's what we see there. And L operating on this pink particular solution gives you the pink g, right-hand side of the non-homogeneous equation that you see there, okay? And so L operating on that sum gives you this right-hand side, which is exactly the right-hand side that you see here, okay? So it is a solution, and that's what the superposition principle is about. That's really nice, because if you take a look at a non-homogeneous equation and you're summing a bunch of, like, you know, simple functions, but a lot of them, what the superposition principle allows you to do is break up the problem. So you'll solve several non-homogeneous equations, one for each simple term, and then get a particular solution for each non-homogeneous equation with a simple term, and then just add up all those particular solutions, and you got yourself a particular solution to the non-homogeneous equation with all those simple terms summed. Okay, that's really nice. And here I write more generally, if L operating on a particular solution gives you gi, then L y particular, where y particular is not just the sum of particular solutions, but constants times a particular solution, sum of that, then you get C1 G1, C2 G2. Okay, what that means is it's not just, you know, they don't just have to be sums. Okay, in this theorem we only considered sums, but if you had C's in front of all of these, okay, then this equation, then YP would be a solution to the non-homogeneous equation with those same C's there. Okay, we could see this with an example to make it clearer. So find the solution of this non-homogeneous equation. Okay, it looks kind of similar to the non-homogeneous equation we considered up here, doesn't it? Right? Almost. Here you have a 2e to the 2x, but here you got an 8. And you know, here you had plus 2x ex minus ex, but here you have these. So what are we going to do? Well, let's write the right-hand side in terms of what we have solutions for. So the right-hand side, you could write it as 4 times 2e to the 2x. And why? Because we know a particular solution that will give us 2e to the 2x, okay? Minus 7 times this, okay? And again, we have a particular solution that will give us that. then this right-hand side is actually just equal to 4g2 minus 7g3 from the previous example. So a y particular will be 4yp2 minus 7yp3. Okay, and yp2 is e to the 2x. Yp3 is x to the ex. Okay, and so here goes your solution there. Okay, there goes your solution. And you could, again, to gain intuitive insight, you could just operate this is going to be bilinearity equal to L but what happens when we operate with L on these? Well, we know what happens because we see the result. This is e to the 2x. We're going to get 2e to the 2x. And we're going to get, when we operate on x e to the ex, well, we look at that's going to be what we got in pink there. Okay. And well, that's precisely the right-hand side there. And L operating on y is precisely the same L. And we had the same L in this example as we do here. Okay, so we just showed that this guy here is a particular solution to the non-homogeneous equation that we have there. It satisfies the differential equation. So I end with a remark here. Linearity is a crucial concept for modeling dynamical systems, as it implies that a superposition of input or forcing functions corresponds to a superposition of outputs or responses. Okay? So you could have something like a forced spring or a source in a circuit. Okay? What this superposition principle tells us is, if we know a particular solution to one input, one force on, say, the spring, okay? And now suppose we put a completely different input, so a completely different G, okay? And we know the response of the system, so we know a particular solution to that G. Then the behavior of the system under both inputs, so you operate now with both of those forces, not just G1, not just G2, but G1 plus G2. You add both of these forces together. Well, what's going to be your response? For a linear system, it's going to be the response that you would get from the first system acting alone, okay, plus the response that you would get from the second system, okay? Inputs, a sum of inputs corresponds to a sum of outputs. That's really nice, okay? And so linearity is very important when modeling, okay? And in general, when you have a linear system, you feel a little comfortable. Non-linearity, well, that gets you into trouble, because you could have one input and you get a certain response, and you have a different input and you get a certain response, and you can't then conclude, well, I'll just operate with both of those inputs and I'll get some predictable behavior that's the sum of both responses. No, you get a whole new beast, okay? Other things start to happen that you might have not predicted, okay? You can't just extrapolate from each single input response correspondence, all right? And so linearity is not something that we're just using to prove these powerful theorems, although that's very important. It plays a very crucial part in modeling.